1.5, applications and modeling with quadratic equations. So again, when we're dealing with applications and models, we're really talking about word problems. So I'm going to be using the PowerPoint slides to help present the word problems so I don't have to write them on the board, but we'll be doing the work on the board and be interacting. So you'll see a little bit of me, a little bit of the PowerPoint, and bouncing back and forth. Hopefully you'll be able to see me in the corner of the screen going through stuff, and then I'll switch over to fully the whiteboard so that we can see us working through the problems. So let's get started. So the first thing we're going to do here is we're going to look at a review of solving applied problems. We've covered this before. It's just the steps that we want to take. So first, we want to read the problem carefully, make sure you understand it, understand what's given and what it's looking for. Okay. After which, assign a variable to represent the unknown value using diagrams or tables as necessary. Write down what the variable represents. If necessary, express any other unknown values in terms of that variable or in terms of variables, and then relate it to that variable. Write an equation using the variable expression or expressions. Solve the equation. Once you've solved the equation, state the answer to the problem, and then look at it. Does it seem reasonable? Does it answer what was asked? And check the answer in the words of the problem. So make sure that that could really be the answer. Make sure that it actually makes sense and that you answered the question that was asked. Far too many times we get through and we're so happy we found solved for the variable that we never actually solved the problem that's been put before us. So let's get into this and look at it as a sample. Okay, so a geometry problem. I'm going to look off to the side because that's where my monitor is and I can see the problem. So a piece of machinery produces rectangular sheets of cardboard such that the length is twice the width. Equal size squares measuring 10 centimeters on a side can be cut from the corners, so the resulting piece of cardboard can be shaped into an open box by folding up the flaps. If specifications call for the volume of the box to be 7,500 cubic centimeters, find the dimensions of the original piece of cardboard. Remember, first time we just read it through and we see, or we try to start understanding. Now I'm going to pull pieces out of it and start drawing some stuff with that. So I'm just going to put my mouse off to the side there so I can do it. So a piece of machinery produces rectangular sheets of cardboard. So first thing I'm going to do, I'm going to draw my rectangular sheet of cardboard such that the length is twice the width. We got length, we got width, and the length is equal to 2 times the width. So I'm just saying L equal to 2W. Equal sized squares measuring 10 centimeters on a side can be cut from the corners. So we're going to cut squares out of these corners, and they're going to be 10 centimeters by 10 centimeters. And that's the same for all of them. Okay? So that the resulting piece of cardboard can be shaped into an open box by folding up the flaps. So we see if we were to cut those out, we can fold up the sides and we have a box without a top. If specifications call for the volume of the box to be equal to 7,500 cubic centimeters, find the dimensions of the original piece of cardboard. So we want to find L equals what and W equals what? What's the length and what's the width? Okay, so this is what we're looking for. So now I'm going to switch over to showing me on the full screen so we can work through this. Okay, so we've got this. We found out that we've got a width. And remember that width is the full distance there. We've got a length, which is twice that width. We have corners that we're cutting out that are 10 centimeters by 10 centimeters. The total volume we're looking for is 7,500 cubic centimeters. We want to find this original length and this original width. So if we're going to do that, we have to go, well, what's the formula for volume? It's length times width times height. Well, I want to get this all in terms of one variable, so we already have a width is W. We have a length, which is 2W, but that's this full width. That's not going to be the width of this completed box. This completed box is going to have dimensions like that, where I can actually go from, say, from here to here, do it as with the arrows just so we don't have the hash marks getting in the way. Well, what is this dimension from here to here? If the full width is W, and each side of this square on the corner is 10 centimeters, then this is 10 centimeters, that's 10 centimeters. So this distance here, what's going to be the width of our box, is going to be W minus 10 centimeters minus 10 centimeters, or it's going to be W minus 20. That's going to be the width of the box we're going to be creating. The length, same thing. Well, we have it in terms of W, so 2W, but it's also going to lose the 10 centimeters and the 10 centimeters. So minus 20. So we have W minus 20, 2W minus 20 for the length and the width. And then the height is going to be the 10 centimeters. So our volume can be written as, and actually I'm going to remember the volume that we're looking for is 7,500. So I'm going to say 7,500, which is V, is equal to L. Our length for our box is going to be 2W minus 20 times the width, which is going to be W minus 20, times the height, which is going to be 10. So now we can start solving for W. Well, the first thing we're going to have to do is multiply through all this stuff. So let's get that done. So 7,500 is equal to 2W times W is 2W squared. 2W minus 20 is, times negative 20 is negative 40W. Negative 20 times W is minus 20W. Minus 20 times minus 20 is positive 400. Plus 400. So all of that is going to be multiplied by that 10. So 7,500 is equal to 20W squared. That's minus 60, but times 10 is minus 600. Minus 600 W plus 4,000. So we got that. Well, if we're going to solve it, we know we've got to get 0 on the one side. So I'm going to move the 7,500 over by subtracting it. So I have 0 is equal to 20W squared minus 600W minus 4,000 minus 7,500 is 3,500. 3,500. Now, I could start with it right here, but I do realize that these are both divisible by 20, so I can cut it down a little more. And I'm just going to move this stuff over to the other side as I do that. So I'm going to say W squared minus 600 divided by 20 is 30. 30W minus 3,500 divided by 20. 3,500 divided by 10 is going to give me 350. 350 divided by 2 is going to give me 175. is equal to 0. So now I've broken it down to something that's a little bit more doable. And I may want to look at it and say, well, is there some, can I find this really quickly? Two numbers that multiply to negative 175 and add to negative 30. So I'm just going to say multiply to negative 175 and add to negative 30. So we just look and see, can I see something quickly? I know that they have to have opposite signs, and the larger one is going to be negative. So I say, well, 35, 70, 105, 175. Hey, that might work. Okay, that was 35, 70, 105, 140, 5. That actually works. So I have negative 35 and positive 5. Well, that saved me going through the quadratic formula or through completing the square. So I can say W minus 35 times W plus 5 is equal to 0. So W is either equal to 35 or negative 5. Okay, so we've got these two values to work with. Now we look at it and say, well, what's the possibility here? 35 and negative 5. Well, the width cannot be negative, right? That can't happen, so that's no good, which means W has to be 35. And then the length is equal to 2 times that, 2 times 35, or 70. So we have W equal to 35 centimeters and L equal to 70 centimeters. Now, let's see if that actually works, or if we made a mistake along the way. So we know that these are correct, so let's see what happens. I'm going to put, so 70 minus 20 is 50. So I have 50. 35 minus 20 is 15. 15 times 10 times that gives us 7,500. So the width, the original width of the box is 35 centimeters, and the original of the, I should say, of the piece of cardboard is 35 centimeters, and the original length is 70 centimeters. So notice I used common sense and looked and said, well, a width cannot be negative, a length can't be negative, so therefore this is the only possible answer. And then I also looked at it and said, well, let's see if that really comes out to what we expect. So I threw the calculation in there, and it did work. It had the width being half of the length, so everything worked out as we would hope. So let's erase this and go on to another application. But notice I drew a diagram so I could see what was going on. I drew a picture. I started putting any information it gave me together and getting pieces of it so that I could come out with the final thing. Now I used W as my variable. Nothing says that you have to use that W. You could use X. If you feel better using X, by all means use X. Just define X as being the width. So that's fine. You could have even done it and said, well, if the length is twice the width, then X is going to be my length and my width is going to be 1/2 X. That's fine too, and you would have come out with X equal to 70 being your length, and then you would have come out with a width of 35. So let's pull up the next problem. If I can convince it to do so. Okay, so we're going to briefly see that problem. We're going to bounce on to the next one. Okay, this one involves Pythagorean Theorem. So a restaurant needs to build an access ramp to an outdoor dining area. The horizontal length of that ramp that the ramp covers is 5 feet shorter than 3 times the height that it covers. The length of the ramp itself is 7 feet longer than the horizontal length. Find the length of the ramp itself. Okay, now, whereas the box problem was something that you really might run into, you need to come up with a box that's packaging science. You need to come up with a box that holds a certain volume. You want to start with a piece of cardboard, but your machinery only has the ability to cut up to 10 centimeter squares off of the corners. Well, and you should say they have to be squares in the corners, otherwise you don't get. So it's a realistic situation. This, on the other hand, I think you'd be hard pressed to find a situation where you'd be given these types of things to figure it out. So, okay, it needs to 5 feet shorter than 3 times. It's not likely. So I'll admit this is an unrealistic problem, but it's a typical type of thing that we show in a math class. There are other problems that will run into these things, but this is what we use. So a restaurant needs to build an access ramp to an outdoor dining area. So it's a ramp. Okay, I got my ramp. Beautiful. The horizontal length of that the ramp covers is 5 feet shorter than 3 times the height. So I've got a height, I'm going to say x is the height. Okay. The horizontal length of the ramp covers is 5 feet shorter than 3 times the height. So this distance here is 5 feet shorter than 3 times the height. So 3x minus 5. The length of the ramp itself, this angled portion of it, is 7 feet longer than the horizontal length. So that's 3x minus 5 plus 7. It's the horizontal length plus 7. Find the length of the ramp itself. We are looking for the length of that ramp. Okay, so let's get the PowerPoint slide out of the way and come back in. So there we go. So we've got x is the height. 3x minus 5 is the horizontal length. 3x minus 5 plus 7 is the length of the ramp itself. Obviously, we can rewrite that as 3x plus 2. So I'm going to do that because that's simpler to work with. Now, we want to find the length of this side. And this is a great example of where we're going to need to pay attention when we get done to get the correct answer, because when we find x, that's going to give us the height. We really don't care about the height. What we're looking for is the length of the ramp. Well, how can we do this? Well, we know that Pythagorean theorem will relate the sides of a triangle to the hypotenuse. So we can say that 3x plus 2 squared is equal to 3x minus 5 squared plus x squared, right? A squared plus b squared is equal to c squared. X squared plus 3x minus 5 squared is equal to 3x plus 2 squared. Now we're going to start squaring things, combining like terms, etc., etc. So we have 3x plus 2 squared. That's a square of a sum. So we square the first term, 9x squared, 2 times the product of them, so that's 6x, so that's plus 12x, plus the square, plus 4 is equal to. Now we have 3x minus 5 squared. That's the square of a difference. So we square the first term, 9x squared. We take minus 2 times the difference. So 3 times 5 is 15x. So we have minus 30x. And then plus the square of the second term, 25. Plus x squared. Don't leave out that part. Now we start combining like terms. 9x squared plus 12x plus 4 is equal to 9x squared plus x squared is 10x squared minus 30x plus 25. Bring them all over to this side. Why am I bringing them over to this side? Well, really because I like to keep that positive leading coefficient. And I see 10x squared here, 9x squared over here. So if I brought it this way, I'd end up with a negative in front. So I'm bringing it to this side. And I got to bring everything over. So I'm going to end up with, so if I subtract 9x squared and subtract 12x and subtract 4, this is going to be 0. So we got 0. 10x squared minus 9x gives you x squared. Minus 30x minus 12x gives you minus 42x. And 25 minus 4 is 21. Plus 21. Okay, and now I look at this and I go, well, I can look and say, what about two numbers that multiply to 21 and add to negative 42? 21 and 1. Anything less than that's not going to make it. So it's not going to get there, okay? We can't do a simple zero product rule. So let's use the quadratic formula. X is equal to negative b, negative 42. And so negative 42 plus or minus the square root of negative 42 squared minus 4 times a, which is 1, times c, which is 21, over 2 times a, which is 1. So negative 42 is 42, plus or minus the square root of, what's 42 squared? $1764. Minus 4 times 1 times 21 is 84. Over 2. So is equal to 42 plus or minus the square root of 1764 minus 84 is 1680. Over 2. Let's see, there's a number of things we could do here. First of all, I do see that I can pull, well, I could obviously pull 4 out of this, but I think I can pull 16 out of this also, because 16 times 100 would give me that 1600, and 16 times 5 would give me that 80. So I'm saying that I can pull 16 out of it. So if I take 1680 and divide it by 16, I get 105 as I thought. So I can say that's equal to, let me get out of the review there, 42 plus or minus 4 square root of 105 over 2. Anything else I can pull out of that? Well, that's 15 times 7. That's not going to do it. So that's 3 times 5 times 7. Yeah, I'm not going to be able to pull anything outside of that, but I can factor out. I can factor out. I got 42, 4, and 2. So I can say that that's equal to 21 plus or minus 2 square root of 105. Okay, so I'm down to that. So what is the square root of 105, just to get an approximate value? And that's going to be 10.25 approximately. 10.25 minus, multiplied by 2 would give me 20.5, so that's possible. And otherwise we go more than that. So let's see what we have here. So we got 21 plus or minus 2 radical 105. So we can have x is equal to, and we switch to a different color just so it's not in the way. And obviously we're going to have to round this. So 10.25 plus times 2, or my whole thing, so I get 20 point, it was actually a little less than that, I had rounded it, but using my whole number, I get 20.49, so 21, so I have approximately x equal to 21 plus or minus 20.49, so x is equal to 21 plus 20.49 is 41.49, and 21 minus 20.49 is 0.51. So either one of those could be valid. Let's see what it was talking about here just to make sure. I'm going to come back and share that because I did not take note of what it was saying for whether it was in feet or what. I think it was in feet, but rather than taking a guess, I'm going to look at that again. Feet. Okay. So it is in feet. And this makes a huge difference. You may go, well, what does that do for me? But if we look at that, now we can get into some reality here. X represents the height. So either the height of this ramp is 0.51 feet or it's 41.49 feet. Common sense tells us there is no way that this access ramp to an outdoor sitting area is going to have an elevation change of 41.5 feet. It's not going to happen. So therefore, we must be talking about that. Not to mention the angle that would be caused by that. If we had this as 41.49, then here we have 150 feet minus that approximately. So we'll call it 125 feet. So 120 feet long and about 127 feet would be the length of that, and you'd be covering 50. Yeah, that's not going to happen. Whereas this makes much more sense. So our final step is we're looking for the length of the ramp itself. So 3x plus 2 is equal to 3 times 0.51 plus 2 gives you 1.53 plus 2, or 3.53 feet is the length of the ramp. And that makes much more sense. I can very easily believe that the ramp to an outdoor sitting area is going to cover a half-foot drop, so basically a little step down that people would normal people could take that step, and be about 3.5 feet long, so it's just a little ramp out, as opposed to this huge 127-foot ramp that's just going to take up all sorts of space and put them out in somebody else's backyard. So there we go. So looking through that, we've got to look at those pieces. Don't forget to pay attention to what units it's in and make sure it makes sense. Here, nothing stopped x from being equal to 41.49 because obviously that could be a length. The only thing that stopped it was common sense saying there's no way that they're going to have a ramp to cover a drop of 41.5 feet. Okay, let's erase this and continue on with another example. Okay, as I share those PowerPoint slides again, coming into your view, getting where I can see it. There it is. Let's get on to the next one. So this is what's called a model. If air resistance is neglected, an object projected directly upward from the ground with an initial velocity of 73.5 meters per second has a height s in meters and time t in seconds. The relationship between s and t is given by the following equation. This equation is a model. It says, given certain input, this is what the output's going to be. So we're modeling this relationship. So we have the following equation is s is equal to negative 4.9 t squared plus 73.5 t. So whereas in the previous two examples, we came up with a quadratic equation to solve a problem, here we're being given a quadratic equation, but it's a model, meaning that it is giving us a relationship between the input and the output, not just an equation to solve for a specific output or a specific input. So this can be used for many different ones. Questions we're being asked are, after how many seconds will the projectile be 100 meters above the ground? And how long will it take for the projectile to return to the ground? So let's go back and put some of this stuff on the board here. If air resistance is neglected, okay, so we're not dealing with air resistance, an object projected directly upward from the ground. So this object is just being shot up in the air with an initial velocity of 73.5 meters per second. So it's going at 75.3 meters per second upwards initially. Obviously, it's got gravity fighting against it, and that's where all this stuff comes in here. Okay. So it's going up initially at, and I would say that's initial velocity, 73.5 meters per second. But we don't really need to take that into account because we're being given a model here. Okay. Has a height s in meters, so s is the height in meters, and a time t, so that's the time in seconds. The relationship between s and t is given by the following equation. So we have s is equal to negative 4.9 t squared plus 73.5 t. Okay. Notice that the 73.5 meters per second that it starts at came into this equation. That 4.9 you may recognize as being half of 9.8. So that's dealing with the gravity fighting against us. Okay, so that's going to come into there. We want to know after how many seconds will the projectile be 100 meters above the ground. So we're saying at what t is s equal to 100. And then the second question, so that's A. The second question is going to be, how long will it take for the projectile to return to the ground? So at what t is s equal to 0, right? If we're at the ground, that's 0. Notice that the constant term doesn't exist. That's because we're starting at the ground level, which is 0. If we started 10 feet above the ground, if we were standing on a step ladder or something and we shot it from above the ground, then we would be shifted up by 10. Some of these things that we can take note of. Okay, so let me get this out of the way so we can zoom in and see what we're doing on the board. Okay, so I wrote these things here. The main things are, we're given a relationship. at what t is s equal to 100. So we're trying to find t when s is equal to 100, and at what t is s equal to 0. So we're trying to find t when s is equal to 0. So start with the first one. At what t is s equal to 100? So we go, okay, 100 equal to negative 4.9 t squared plus 73.5 t. Well, we want to get them all on the same side. You know me, I like to have a positive leading coefficient if possible, so I'm going to move them over to this side. So I have 4.9 t squared minus 73.5 t plus 100 is equal to 0. Now that we've done that, I don't like to make things any more painful than they have to be. So I'm just going to plug this into the quadratic formula. I'm not going to try dividing everything by 4.9 and seeing if I can do anything else. I'm not going to do completing the square. So I'm just going to start plugging in. So x is equal to negative 73.5 plus or minus the square root of negative 73.5 squared minus 4 times 4.9 times 100 over 2 times 4.9. Okay, so we got those values. I'm going to grab my calculator so we can do these things. So x is equal to 73.5, negative is positive, plus or minus the square root of negative 73.5 squared, so 73.5 squared, that's 5402.25, minus 4 times 4.9 times 100, 4.9, 100, gives me 1960, all over 2 times 4.9, which is 9.8. So 73.5 plus or minus the square root of, so we got 5,402.25 minus 1960 gives me 3,442.25, 442.25 over 9.8. Well, I'm trying to find a height. I'm going to have to take the square root of that. So approximately 58.67. So I've got is equal to 73.5 plus or minus 58.67 over 9.8. So now I can do both these. And what am I looking for? I'm looking for what time is s equal to 100. Okay, so we're going to take 73.5 plus 58.67 and divide it by 9.8. And we're going to take 73.5 minus 58.67 and divide it by 9.8. So 73.5 plus 58.67 gives us 132.17. Divide that by 9.8 gives us 13.49 seconds. I'm going to get rid of that for a second because I also want to get the other one. And if I subtract 73.5 minus 58.67 gives us 14.83 divided by 9.8 gives us 1.51. So those are both in seconds. Now it gave us two values. They're both positive. Well, what does this mean? The question is, at what time is s equal to 100? The reality is that's at 13.5 seconds and 1.5 seconds. Because remember, it's a projectile. It's going to go up, it's going to pass that point, it's going to come back down. So it's going to happen at both times. Let's just make sure that the question didn't want us to say specifically when it was going up. Did it just ask for the time? So it says, after how many seconds will the projectile be 100 meters above the ground? Now, my interpretation, I would look at that and say, well, that's probably saying after 1.51 seconds, it will be above the ground. But in reality, it will be 100 meters above the ground at both of those times. Now let's go to the second part of this. Trying to unshare that, there we go. Which is, at what time will it hit the ground again? Well, let's go to blue here. Well, that means we're going to set this equal to 0, which I'll just do that over here. 0 equal to negative 4.9 t squared plus 73.5 t. Well, I can just divide through by -1, giving me 4 where I subtract, move both all over to this side. So 4.9 t squared minus 73.5 t is equal to 0. Well, now I can factor, actually a relatively easy way, I can factor out the t. So I've got t times 4.9 t minus 73.5 is equal to 0. And then this one I can find, so t is equal to 0, which makes sense. That's the starting time, right? When it first shot up, it started at ground level. So at t equal to 0. The other one, 4.9t minus 73.5 equal to 0. Add 73.5 to both sides. 4.9t is equal to 73.5. T is equal to 73.5 divided by 4.9. T is equal to, and I'll put the little second there just because I'm there. Grab the calculator. And I get 73.5 divided by 4.9 gives me 15. So when does the object end up back on the ground? At 15 seconds. So it was in the air for 15 seconds. At 1.51 seconds, it hit 100 meters. At 13.49 seconds, it came back down to 100 meters. At the very beginning, it was at ground level. At the end, it was at ground level. And I will point out, remember, we want to look for common sense and does this answer work? Yes, we expect that when it goes up, it's going to hit a certain level and then go beyond, and then it's going to come back down again. So that's one piece of it. Also, notice that it took 1.51 seconds for it to get from the ground level to 100 meters. It then took 1.51 seconds to go from 100 meters back to the ground. 13.49 plus 1.51 is 15 seconds. So it does make sense. So that's good. We see that, okay, it does seem to be going up and down. And remember, we neglected air resistance and everything. So therefore, you're just looking at acceleration due to gravity, the initial velocity and the final velocity, which means when it hits the ground, it was going 73.5 meters per second down at that more instantaneous time when it hit the ground. Okay, let's erase this and go for one more thing, I believe. So, get this out of the way. Let's share that screen again. Okay, another example, modeling with quadratic equations. So, based on figures from the period 1992 through 2003, the quadratic equation S equal to 0.00579 x squared plus 0.2579 x plus 0.9703 models sales of SUVs where S represents sales in millions and X equals 0 represents 1992, so the year 1992, X equal to 1 represents 1993, and so on. So basically, X is the number of years from 1992 or after 1992. Use the model to determine sales in 2002. Compare the results to the actual figure of 4.2 million. And according to the model, in what year after 1992 did sales reach 3.5 million? Round to the nearest year. So based on figures from 1992 to 2003, the quadratic equation, so I'm going to write that down. S equal to 0.00579 x squared plus 0.2579 plus 0.2579 x plus 0.9703, get the plus 0.9703. So there's our model. S represents sales in millions. S, sales in millions. X represents number of years after 1992. Use the model to determine sales in 2002. S in 2002. And the second part, according to the model, in what year after 1992, what year did sales reach 3.5 million? Were sales 3.5 million? Or reached 3.5 million. So it could be above 3.5 million. But we're looking for that year. And it says round to the nearest year. So I'm just going to put that nearest year. Okay. So let's get back to this whiteboard so we can do this. Okay. So we have this quadratic equation or quadratic formula, this relationship model. We know S stands for sales in millions, X stands for the number of years after 1992. We want to find what the number of sales in millions are in 2002, or the number of sales in 2002. So that just means if we're looking for sales in 2002, X stands for the number of years after 1992. 2002 minus 1992 is 10 years, so X equal to 10. So we can just plug that in. S is equal to 0.00579 times 10 squared plus 0.2579 times 10 plus 0.9703. 10 squared is 100. So that's going to move us the decimal place over 2 places. So it's 0.579 plus times 10 is going to move the decimal place over 1 place. 2.579 plus 0.9703. Now I'm at the point where I'm going to use a calculator just to make sure I tell you the right number. So we have 0.579, 2.579, and 0.9703 added together gives us 4.1283 million, or approximately 4,128,300 SUVs sold in 2002. Okay, what's the next one? what year were sales 3.5 million? Or did they go over 3.5 million? Well, we already see that in the year 2002, so 10 years afterwards, they reached 4.1 million. So we know it's going to be less than the year 2002. So it's going to happen before that. But we work our way through it. I'm just going to put a line here to separate it. My black marker seems to be working a little better than my blue one. So I'm just going to continue on with that. So we're looking for 3.5 million. 3.5 million is equal to 0.00579x squared plus 0.2579x plus 0.9703. Well, if we want to do this, we're going to move the 3.5 over to the other side. So it is equal to, so 0 is equal to 0.00579x squared plus 0.2579x minus, so 3.5.9703, so minus 2.5297. And now we're going to go through the quadratic formula. So x is equal to negative 0.2579 plus or minus the square root of 0.2579 squared minus 4 times 0.00579 times, oops, got squiggly instead of a parenthesis, times negative 2.5297 over 2 times 0.00579. Never said it was going to be a lot of fun plugging these numbers in, but when you do this, so now I can start plugging numbers in. So x is equal to negative 0.2579 plus or minus the square root. Now I'm going to save myself a little time and I'm just going to do this whole thing all in one shot rather than writing out the different things. So I have 0.2579, which when I square it, I get 0.06651,241. I've got minus 4 times 0.00579 times negative 2.5279. So 4 times 0.00579 gives you 0.02316. Multiply that by negative 2.5297. Just making sure. 2.5297 puts us at negative 0.58587852. When we're subtracting that, so that gives us positive. So we have 0.06651,241 minus 0.058587852. So that's going to be added together. Gives us 0.125100262. 0.125100262 over, again, just 1 second here. So, okay. Okay, so 2 times 0.00579 gives us 0.01158. 0.01158. Okay. There's that. Now we can take this and add this or subtract it. So what is the square root of that? So we're looking at x is equal to negative 0.2579 plus or minus, I'm going to take it only to 5 decimal places because that's how far the bottom one goes, 0.3536, well, we'll take it to 4 decimal places because it's going to round there anyway. 0.37 over 0.01158. Okay, now I do notice something here. I have a negative value here. And if I make this one negative, I'm also going to end up negative, which we're looking for what year? Well, obviously it can't be before 1992, so this has to be a positive value. So we're going to use only the positive one, so I can take that 0.2, I can take my negative 0.2579, add 0.3537, and then divide by 0.01158. So 0.2579, that's negative, plus 0.3, be careful about that, 0.3537 plus gives us positive 0.0958. Divide that by 0.01158 gives us 8.27, approximately equal to 8.27. Okay, and it says what years were sales over 3.5 million, or did they reach 3.5 million? Well, at 8.27 years is where it actually hit 3.5 million. This says to the nearest year. So technically, we would say year 8, because it does say to the nearest year, but it wasn't until year 9. So I would say the answer should be 9 years, so that would be 2001. 1992 plus 9. It didn't reach it in the year 8. It took until a quarter of the way into year 9 before it reached it. So there we go. So yet another model with quadratic equations. So as we can see, we can model things with quadratic equations. We can go through and we can come up with, we can use quadratic equations to solve things for certain real world applications and some made up applications. But there's a lot of work that can be done with quadratic equations.